It weighs more than 20 fully loaded Boeing 747s. It stands taller than the Statue of Liberty. And it runs on engines so powerful, they can each produce more thrust than a space shuttle main engine. And in May of 2024, it nearly tore itself apart trying to come home. But here's the thing nobody is talking about. That explosion was not a failure. It was data. 7 months. That's how long SpaceX went dark before lighting Starship's engines again. 7 months of rebuilding, rethinking, and reimagining one of the most complex machines ever constructed by human hands. And the question hanging over every engineer, every space agency, every astronaut waiting for their seat was simple. Is Starship actually getting better? Or are we watching the world's most expensive fireworks show? Because let's be honest, the critics weren't wrong to ask. The first test flight in April 2023 ended in a launch pad destroying explosion that sent a shockwave through South Texas. Flight 2 blew up before stage separation. Flight 3 managed to reach space, then tumbled and burned during re-entry. Flight 4 finally showed a controlled descent. Flight 5 caught the booster, with metal arms, mid-air, like something out of science fiction. And then, silence. 7 months of silence. When Flight 12 finally lit up the skies over Boca Chica, Texas, the entire world was watching to see if SpaceX had truly cracked the code. Before we talk about the flight itself, you need to understand why this test was different from everything that came before it. Because this wasn't just another Starship on the pad. This was a completely rebuilt system, top to bottom. Let's start at the bottom, literally, the booster. Designated Booster 14, this Super Heavy carried 33 brand new Raptor V3 engines. Now, the V3 sounds like a minor upgrade. It is not. SpaceX engineers redesigned the engine to be lighter, simpler, and more powerful, pushing well past 280 metric tons of thrust per engine. The entire engine bay was reworked to pack these 33 monsters more tightly, which directly translates to a faster, more aggressive liftoff. And you could see it. Flight 12 climbed off the pad noticeably faster than its predecessors. A visual reminder that power matters when you're trying to drag 5,000 tons off the Earth. The launch pad itself was rebuilt from scratch. The original pad was nearly destroyed in Flight 1. What replaced it is a hardened, water-cooled steel plate system designed not just to survive a single launch, but to support rapid, frequent relaunching. SpaceX engineers demonstrated something remarkable during the fueling sequence. The new system loaded propellant dramatically faster than before. That speed is not a minor operational convenience. For a fully reusable rocket designed to launch multiple times per day on the way to Mars, fueling speed is mission success. And finally, the Starship upper stage itself. Redesigned heat shield tiles, updated propulsion, improved software, a new payload bay with active deployment mechanisms. This was not the same ship that flew before. On the first launch attempt, the rocket was ready, the pad was ready, the world was watching. And then, a fuel loading arm on the launch tower got stuck. One arm. That's all it took to scrub the entire attempt. To some, that looked like incompetence. But if you understand launch operations, it's actually a testament to how seriously SpaceX takes their pre-launch checklist. You don't push through a mechanical anomaly on a vehicle this complex. You wait. So they waited. And on the second attempt, everything went nominal. The engines lit, the ground shook, and Starship climbed. Liftoff was immediate and assertive. The Raptor V3 engines produced a roar that was felt, not just heard, for miles in every direction. The vehicle climbed cleanly through max Q, the point of maximum aerodynamic pressure, where the atmosphere pushes hardest against the hull. No drama, no unexpected vibrations, a clean ascent. Then came hot stage separation, a maneuver where the upper stage ignites its own engines while still attached to the booster, using the exhaust plume to push the two stages apart. On earlier flights, this was one of the most nerve-wracking moments of the mission. On Flight 12, it worked. Clean separation, clean ignition. But then, the booster tried to come home. And this is where Flight 12 gets complicated. After separation, the Super Heavy booster was supposed to execute what's called a boost-back burn, reigniting its engines to flip its trajectory and begin the journey back toward the Gulf of Mexico. On this flight, SpaceX was not attempting a tower catch. This was a water landing test, less ambitious but still technically demanding. The engines attempted to restart, and they failed. Not all of them, but enough. Multiple Raptor V3 engines refused to light, or lit and then shut down unexpectedly. The booster, enormous, powerful, and now uncontrolled, began to tumble. Without engine thrust to control attitude, there was no recovery. The vehicle broke apart in a brilliant, violent fireball over the Gulf. Now, here's what you need to understand about that explosion. The booster's destruction was catastrophic, but the data it generated was priceless. Every millisecond of that failure was recorded. Every sensor reading transmitted back to SpaceX mission control before the signal was lost. Engineers now know exactly why those engines didn't restart, and that means they can fix it. That is the entire point of these tests. Meanwhile, 60 miles above the Earth, the Starship upper stage was having one of its best days ever. One engine failed shortly after separation. That's not ideal, but it's also not a catastrophe on a vehicle with 6 Raptor engines. The ship compensated, maintained stability, and continued accelerating toward near-orbital velocity. Near-orbital velocity, let that sink in. This spacecraft, the largest ever built, came within a hair of entering orbit. That is not a small achievement. That is a civilizational-scale technological milestone, achieved on only the 12th flight of a vehicle that, less than 2 years ago, destroyed its own launch pad on the first try. But the upper stage wasn't done showing off. SpaceX deployed 20 mock Starlink satellites from the payload bay, the first time this deployment mechanism had ever been tested in a real flight environment. The satellites were equipped with cameras that captured footage that can only be described as stunning. Starship floating in the black of space, Earth curving below, the sun blazing against polished steel. These weren't just pretty pictures. They were a proof of concept for the entire Starlink V3 deployment architecture. The system SpaceX will eventually use to launch hundreds of satellites per mission. Then came reentry. The upgraded heat shield performed remarkably. Previous flights showed tiles cracking, burning through, shedding. Flight 12's heat shield held with unprecedented integrity. The vehicle sliced through the upper atmosphere at hypersonic speeds, plasma wrapping its nose, temperatures exceeding 4,400 degrees Celsius, and it survived. The final controlled splashdown attempt in the Indian Ocean was executed successfully. The ship hit its target descent profile. It was oriented correctly. It came down in a controlled manner. And then it exploded, which, again, was expected. SpaceX was not attempting a powered landing. The ship impacted the ocean at terminal velocity after the planned splashdown. That's the protocol for these early tests. The miracle isn't that it exploded. The miracle is everything that didn't go wrong before that point. So where does this leave us? Flight 12 confirmed several things that matter enormously for the future of space exploration. 1. The launch pad works. The rebuilt infrastructure held together under the stress of a full Raptor ignition sequence. That means SpaceX can attempt rapid relaunch cadences, which is critical for their economic model. 2. The upper stage is maturing fast. The Starship spacecraft flew through the most demanding phase of any mission, re-entry, with an upgraded heat shield that performed better than any previous flight. Payload deployment worked. The descent profile was clean. 3. Raptor V3 engine restart reliability is the next frontier. The booster failure wasn't random. It pointed directly at a known engineering challenge: restarting cryogenic rocket engines in space, in a post-combustion environment, under rotational stress. This is a solvable problem. SpaceX has solved harder ones. And 4. The roadmap just got shorter. Before SpaceX can attempt another booster tower catch, they need reliable engine restart. Before they can fly orbital missions, they need a full end-to-end vehicle recovery. But Flight 12 pushed the boundaries of both farther than any flight before it. The moon missions under NASA's Artemis program require a working Starship. Mars requires a working Starship. A future where humanity is multiplanetary, the vision that drove SpaceX's founding in the first place, requires Starship to work. And it is beginning, haltingly, explosively, magnificently, to work. In 1903, the Wright brothers flew 12 seconds. 12 seconds of controlled, powered flight at Kitty Hawk, North Carolina. Most people thought it was a stunt, a toy, a distraction. 66 years later, humans walked on the moon. We are living through a moment that future generations will study the way we study Kitty Hawk. And like those 12 seconds at Kitty Hawk, the explosions, the setbacks, the stubborn arms that won't move on launch day, none of it will be what history remembers. History will remember the day this machine finally reached the stars. And based on Flight 12, that day is closer than you think. Every flight gets them closer. And we are going to be here covering every single one. If this video gave you something to think about, hit subscribe. We cover the science, the history, and the raw engineering behind humanity's most ambitious machines, every week. Drop a comment below. Do you think SpaceX will successfully catch the next booster with the tower? Or will Raptor V3 reliability issues push that back further? The best comments get pinned. Let's talk about it. And if you want to go deeper, watch our full breakdown of how the Raptor engine actually works. I'll see you in the next one.